1, 2, 3. Greetings!
Attitude for timing.
Alright, today we're going to kick off first semester by talking about, it's not first semester, it's second semester, by talking about triple integrals. So we all remember in first semester we discussed integrating over an area. We're doing triple integrals, so we'll be integrating over a volume. So you'll notice it's, instead of dA, it's dB.
Sorry, I was just in the chat. Please.
And our function will be of 3 variables instead of 2. And because it's a function of 3 variables, it's a triple integral instead of a double integral. We're going to start off integrating over boxes. So in the x, in the y, and in the z. And then we'll move on to integrating over more complicated volumes that have more interesting curves and things going on with them. And chapter 12, we'll go through 12.9, and then we'll do an assessment on that. So we're going to first consider integrating over a box, which just has numeric dimensions. So the first dimension references in the x, and then in the y, and then in the z. So the corresponding integral will just look like this, where we have a function in terms of the variables x, y, and z, and then dx, dy, dz. The order is interchangeable because when we calculate volumes, you can calculate a volume in terms of length times width times height, height times length times width, any order is fine. And we also learned in terms of Fubini that any order is fine, so it's still fine with triple integrals. So if we have an example of this,
Why are you Ruby interrupting us?
we are going to evaluate the triple integral of x, y minus y cubed with respect to volume, and our cube in our x is from -1 to 1, and our y is from 0 to 2, and in our z is from 0 to 1. So I'll just fill in those dimensions. Now, I could have chosen any order that I wanted first. I chose to do dz on the inside because my integrand had no z's. So the first integral will just be me adding the z to that. So I'll just have x, y, z minus y cubed z from 0 to 1. So that's going to be xy minus y cubed, so essentially keeping it unchanged. So then it's the double integral dy dx with respect to y. I get x y squared over 2 minus y to the 4th over 4 from 0 to 2. And then I get 2x minus 4. And 0 components, really easy there. And lastly, from -1 to 1 of 2x minus 4 dx. And we'll just get x squared minus 4x.
Minding my business.
It looks like the integral is going to be -8. Now, it's tough, gentlemen, to recognize what this means because you're integrating over a volume, which means dimension-wise, you're one up from a volume, which doesn't make any sense geometrically anymore. So we're kind of beyond the realm of a geometric interpretation, which is hard. So you're just kind of beyond it. If our integrand would have been 1, so that triple integral 1 dv, we'd actually be finding a volume. But if the integral is not 1, we're not finding anything we can really imagine geometrically. We're beyond that. Now, if we get creative and don't just do a box, so we're not integrating over a box, that means our bounds will no longer be numeric. And so in this case, we have surfaces that are going to make up our boundaries. So here we look at 2 surfaces that are going to be parallel, in this case, to the xy plane. And so in this case, our planar boundaries, in that they're parallel to the xy plane, what we would want to do is integrate with respect to z first. And so in this case, we'll do dz on the inside. That'll be our furthest inside. And then going outside, you can do dx or dy second or first, depending on what the resulting region looks like. And when you look at this resulting region, that is region D on the xy plane. And we do the same thing we did first semester, is we scan it with respect to x and with respect to y, and make a decision as to which to do first, x or y, to see which one is better. But you look at which region it has parallelism to, or which plane it has parallelism to. This is parallel to the xy plane. If it's parallel to the xy plane, you'd have to integrate with respect to z first. If it has parallelism to no plane, you have to then cut it up. Okay? Slice it, and then do 2 different triple integrals. And we've had to do that before if we did double integrals. So we'll get some practice with this as we get more advanced. So that's what the triple integral looks like, doing with respect to z first. And then we have dA, which is the region in the xy plane. So here's an example. We're going to evaluate the triple integral, where the integrand is 2x dv, where E is the region under this plane, 2x plus 3y plus z equals 6, that lies in the first octant. So I'm going to set this up how it was presented. So, and because it's in the first octant, I could really do this a number of ways, but since we are talking about this with respect to over the xy plane, I'm going to solve for z here. So solving for z, I get 6 minus 2x minus 3y. So that helps me to know my bounds. So when I look at the way this would look, it's the double integral over the region D of, in the first octant, because I'm in the first octant, which means everything's positive. So it's 0 to 6 minus 2x minus 3y. So when I'm looking at in the xy plane, on the xy plane is 0. So it's from 0 up to that plane. So 0 to the plane, and here's our plane equation. So this is solved for z, okay? Which means I'm integrating with respect to z first. So it's the integrand of 2x dz. So that's what I do first, and then dA. And A is the area of the region D in the xy plane. Saying a lot of letters, I'm sorry. Let's draw D though. So to find D, that is the shadow of this plane in the xy plane. So picture you have this plane, which is like a, it's like slicing through space, and you're looking at the shadow of this plane in the xy plane. So if you look at the xy plane, you're looking at when z equals 0. So z equals 0, you would get 6 equals 2x plus 2y. 3y, yep. So here is the region D. That's what they call it, D. And if I look at the x-intercept is 3, y-intercept is 2. So it's an easy way to graph this shadow of the plane in the xy plane. We'll make it look like a shadow. Here we go. So we have the plane slicing through space. This is the shadow of it in the xy plane, and this is the volume. Okay? And that's the shadow of that volume. And so what we have to do is find the boundaries of that, and that's going to define D. Does it matter if I integrate with respect to x or y first here, or could I do either? You could do either, yeah. Because with x, I have a definite lower bound and upper bound. The lower bound would be 0. The upper bound would be this line. With y, sorry, I'm doing y first. Same thing. They both have a good definite upper and lower bound. So I guess it doesn't matter. So if I solve for y, I'll just do that because we're used to seeing things in Silverner's form, us being Americans and all. So x, y would go from 0 to negative 2/3 x plus 2. X will go from 0 to 3. And because I graphed it well, I can see those boundaries. Y 0 to the line, x 0 to 3. Questions on those boundaries? So looking at this, I might as well just do this inner part first. So I'm integrating that with respect to z, which since there's no z in my integrand, I just tack the z on. But then my boundary, my first boundary is kind of ugly. It's 6 minus 2x minus 3y to 0. So that's 2x times 6 minus 2x minus 3y, and then minus the 0, so that goes away. And that's the double integral of that dA. So then I'll plug in my boundaries, which I found over here by calculating the shadow in the xy plane. And I'll just do that distribution. All right, any questions? Okay, so integrating with respect to y. Oof. Okay, so I'll plug in those bounds for my y's. This is going to be a simplified version of that plug-in. So that'll be plugging in that for y and simplifying. It requires a little bit of algebraic manipulation because you have this squared and then you have the fraction. So I kind of did all that ahead of time, so I wouldn't have to take us through that. Okay. And if we do the integral of that with respect to x, polynomial, all of these.
Oh, I'd say.
What's that?
Never mind. I think. Yes, since that's squared or no, it's cube. What's cube? 20 squared.
Thank you. So we got 27 minus.
Like primarily you're very concerned during that class.
It's not everyone's sport.
I know
Maybe you can follow the soccer after.
All right. So we're staying focused. And that's what it looks like. It's just a plane. And that's not the value of the integral, it's just the volume if you go under that, that you're integrating over. Yep. The result?
Yeah.
No. The result is unable to be described using geometry. Yep.
if you like did this or like divided this by the volume, would it give like something geometric then? Like how it's like average height of a rectangle then? Would it be like
We get 2x. Like in that equation, it's 2x dv. So if you're integrating with respect to that, when you divide by p, you get 2x.
I don't think so. Because that would indicate like you did nothing.
You put b in there.
well, because then if you just multiply by the volume. Oh wait, no, yeah. Well,
So if you found the volume,
no, because we're doing it
Maybe the volume in each, maybe the volume in each x value or something. So maybe it'd be like
that's just
the average value of
yes, the average
X.
value of the volume, but like I don't get like what that means.
the average value
Is that a
of 2x.
four-dimensional?
Probably four-dimensional.
that would require some thought. IDK. All right, get started, please.
Oh.
Wait, you stopped recording already? Okay. Guys, goodbye on 3.